of the matter is considered. Calculate the mean molecular weight with or without this approximation. So have you tried this?
Yes, yes.
See, basically what I wanted to highlight was the fact that, for higher elements, I took Z is roughly 1 by 2.
Yeah.
Sorry, Z by A is 1 by 2. Now, it is not exactly 1 by 2. Now, I wanted to highlight why this is a good approximation. It's a good approximation because this approximation is there only for higher elements, and higher elements anyway form a very small percentage. Like here, 74.75 and 24.75, leaving just 1% in beryllium. So the component where the approximation applies is actually a very minor component and hence will not affect the result significantly. Is that okay?
Yeah.
Is that fine?
Yeah, but my result otherwise, maybe I had done some mistakes. So the change was around, the difference without and with using the approximation, the difference was around 0.3. Maybe I had done some mistakes.
Large.
Yeah, I was actually puzzled about it. I'll check the calculation.
No, wait. 0.3, is it?
Yeah, around 0.25.
Probably okay,
0.245.
See, because usually, I mean, in reality, these beryllium and all are much smaller than 1%. Okay, so yeah, maybe, see, because beryllium is 1% and you are making an error of how much?
0.25.
1 by 10. Because instead of 4.5 by 9, when 4 by 9, you're taking 4.5 by 9. Right?
Yeah.
See, Z by A is 4 by 9. When you say Z by A is 1 by 2, you're taking it as 4.5 by 9. So the error which you are doing is 0.5 by 9, so it's 1 by 18. So it is 5% error in 1% of the material.
Yeah.
So yeah, so that is the thing. So it's 0.05, probably much smaller than that, I think. Just check it again.
Yes. I'll check
You understand the whole philosophy now, because you have 1% of the material in which is an error of
5%.
5%. So it is 1 by 100 into 5 by 100.
Yeah, you probably have done some calculations.
5 parts in 10,000,
And probably less than that because you have assumed 1 by 18 is 5%.
Yeah.
I'll check the calculation.
Just check the calculation. Okay. Repeat the above calculation. The fraction of these elements is calculate the mean molecular weight with and without approximation. Okay. Yeah, okay. Then a spherical cluster of stars of radius, velocity dispersion. Is this okay? It's just a real theorem.
But the second part is something I had doubt on. So.
Okay. This probably I will take it. Yeah, basically what you need to do is, see, if suppose all the atoms are static, then you will get a perfect line spectrum. The moment they are moving, the atoms will undergo Doppler shift.
Yeah.
And so there will be a small deviation from the central wavelength.
Yeah.
Okay. So if you have a distribution of velocities, you will have a corresponding distribution of central wavelength.
Yeah.
Okay. So something like you have to use a Jacobian, that probability of having velocity v dv is equal to probability lambda delta lambda, and then relate lambda and v. Okay.
But this velocity distribution was given to the stars, right? So I was confused how to correlate to the
No. So what you do is the following. Yeah, I understand. So you say that, okay, Right. So what you are saying is, I mean, you are saying that the star is having a line spectrum. See,
Yeah.
okay, so the spectrum will become broader in the star because of thermal velocity. But if you take the whole galaxy, it is primarily because the velocity dispersion of stars itself. Right?
Yeah.
Yeah, so that is the thing. So you just suppose that each star is emitting, perfectly aligned emission. Okay. And then what will happen is okay. And now the Doppler thing will depend only on the line of sight. So you have to take, so although the velocity is isotropic, the velocity perpendicular to your line of sight will not lead to Doppler shift, only the component parallel to the line of sight. So you need to find out what is the contribution from there. Okay.
Yeah, got it. But it was given that velocity is same across all the directions.
No. Velocity is isotropic in all directions, but in Doppler, it is
It is
only the
parallel component.
projection of the velocity which will be important.
Yeah, but then we need the angular position of that particular cluster, right? Then.
No, I don't, because I say it's isotropic, no?
But to take the projection, we need some angle, right?
Yeah. So you need to take the angle and then average over that angle, because at different angle, different Doppler shift will be there. No? Okay, so for example, let us see if it misbehaves again. I have this observer and I have one star which is moving in this direction. Okay, and say at an angle theta. So this velocity will be v theta is equal to v cos theta. There will be another one moving like this. So the point is, the ones which are moving like this will not contribute at all. So that is why it will not be uniform distribution. Do you get that?
I guess
you
so.
See, it is like this. You have to, okay, what you need to do is you need to calculate, if suppose there are n of them in different directions, then you need to calculate the solid angle corresponding to a given theta, and then multiplied by the solid angle. That will be the probability of the stars moving in that direction. Okay, I will do this in detail then.
Yeah,
yeah.
Or at least later on can send up handout or something.
Yeah.
Only for this problem. Yeah.
Okay. And then spherical ball of hydrogen atoms of density undergoes. Okay. This is okay, right? I mean, this I already done it. I mean.
Yeah, this was trivial. I was able to do it.
Yeah. Is it okay by everybody?
Yeah.
Okay. Okay. So now let us just continue with the next topic, which I plan to do. And which is that? January, right? Yeah. Okay, so let's start. Can you see the screen?
Yes.
I can.
Yeah.
Yes.
So now, till now, we have been talking about spherically symmetric configuration hydrostatic equilibrium. And here, P of R is pressure, rho of R is density, and these are at a distance R from the center of the system. And M of R is a non-local quantity, it is a mass within a radius, unlike pressure and density, which is at a distance r. And in hydrostatic equilibrium, I know that the derivative of the pressure with respect to radial derivative, there's a gradient, will be given by this. So for the balance between gravity and pressure, and we need to augment it with boundary condition. What is the boundary condition? See, I have demanded that the system should be in equilibrium. It means that at every point, forces have to balance. At the surface of the star, the internal and the external pressure from outside is zero, because ideally outside the star there is vacuum. So if the pressure inside the star at the surface is not equal to zero, then there is a pressure imbalance. In order to make sure that there is an equilibrium, I need the pressure on the surface to be zero. Is it clear?
Yes, yes.
Okay. Now, this looks like a very harmless kind of an equation, but there are only very specific cases where this equation can be solved analytically. And what we will focus on is a class of models, some of which can give analytic solutions. Okay, so this is going to be the aim of today's talk. Okay, fine. So now, if you have, so and this class of models for which I will calculate this, I will do this exact analytic calculation, is something called the, okay, just a minute. Okay. So for these models, we have the pressure going as a constant times rho to the power gamma. Now, for certain, suppose it is a monatomic gas and gamma is 5/3, then it is an adiabatic law, right? PV gamma equal to 1 is equal to constant.
Yes.
Okay. But now, so now I am saying that I take any gamma which is a constant, so not necessarily adiabatic. Now, for no, now it is writing okay, I don't know. For monoatomic gas, if gamma is equal to 5/3, it is adiabatic. Now, on the other hand, suppose I have an ideal gas. Suppose it is an ideal gas. With gamma equal to 1. What does it mean? It means pressure is proportional to density. And I know that for an ideal gas, P equal to nkt, number density n, which is equal to rho by mass of the particle into kT. So if P is proportional to rho, it implies that T is a constant, which means it is a system where the temperature is same at all points in isothermal system. So different values of gamma can give you different physical situations. Is it clear?
Yes.
Okay. So now let me consider a generic gamma for which gamma is greater than 1. Now, here it is equal to 1, which is a limit, and I'll tell you why there is a problem with this, which I'll come. It is called the singular isothermal sphere. Okay. So now let us consider this one. So we have dP by dr is equal to K gamma d rho by dr. Oh, my r and gamma is having problem. Huh? Okay. So let me do something. So I will call it dp by dr is equal to, oh no, this will create another, no, okay, this is dr. Okay, this is equal to uh, 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 k into gamma into rho power gamma minus 1 d rho by dr. Okay. And this is equal to minus gm of r rho r by r square. Now here I will do one thing. I will try to convert this whole thing into a pure differential equation because, as I said, this is not differential equation, it's an integral differential equation because here m of r involves an integration of over rho of r. So I can write this as dp by dr is equal to minus g. I will initially write it as m of r rho of r square. I take r square and rho on the other side. This implies r square by rho dp by dr is equal to minus g m r. And now I will differentiate it. If I differentiate it, I will have d of r square by rho dp by dr is equal to minus g. What is dm? Dm is basically rho of r 4 pi r square dr. Are you with me?
Yeah.
This is dm. Okay. And so I can write this in a slightly different form, which is dr square by rho dp by dr, this by dr 1 by 4 pi r square is equal to minus g rho of r. Okay?
Yeah.
Now, so you see what has happened. It has become now a second order differential equation. And this is the price you are increasing the order of the differential equation is the price you are paying for converting this integral equation into a differential equation. Because here, this m of r has an integration. It is to remove this that you need to convert into a second order differential equation. So this is what you get. Okay. And now I can substitute P is equal to K rho power gamma. And then if I substitute that from what we have got, we will get 1 by 4 pi r square. I keep writing this r square here out of habit like this. R square, 1 by, so d by d r square by rho. And then I have k gamma rho gamma minus 1 d rho by dr is equal to minus g rho. Okay. And now this can be written as, so this can now be written as in a slightly different form. It will be 4 pi r square d by dr r square by rho. Kappa k comes out. I have, and gamma also comes out because it's a constant. And so I have rho power gamma minus 1 minus 2 d rho by dr equal to minus 0. Okay, I mean, this is just some dry solution, but this is to be done for getting it into a very interesting form. Oh, sorry. This will not be. Okay. Now, what I will do is, let me introduce a new variable, xi, which is a dimensionless variable and is equal to r by alpha. Now, alpha has dimensions of length. You can ask, what is alpha? Now, right now, I will just keep it as a constant of dimension length. Later, I will choose alpha in order to simplify my equation. Okay. So, this and this together will give me gamma k by alpha cube 4 pi xi square d by d xi and into alpha square xi square rho to the power gamma minus 2 d rho by alpha d xi. Okay, equal to minus 0. And now what you see is, so you have an alpha cube, an alpha square and an alpha. So I can rewrite this as 1 by 4 pi alpha square gamma k d by 1 by xi square d by d xi square rho gamma minus 2 d rho by d xi is equal to minus 0. Are you with me?
Yes. Yes.
Okay. Now I will, in order to simplify this further, I will reparameterize gamma in a particular way. Now, gamma, I always want to be greater than 1. Okay. Alpha, gamma equal to 1 is the ideal gas situation. Okay. Suppose gamma is always greater than 1, then I can write gamma as 1 plus 1 by n, and gamma greater than 1 always implies that 0 is less than n is less than infinity. That is, n is always positive. Am I right? Because
Yes.
if gamma is infinity, then n is 0. And when gamma is 1, sorry, when gamma is infinity, n is 0. When gamma is 1, n is 0. Sorry, n is infinity. So when gamma is equal to 1 implies 1 by n is equal to 0 implies n equal to infinity, and gamma equal to 0 implies gamma equal to, no, gamma equal to, not gamma equal to 0, I'm sorry. And gamma equal to infinity implies n equal to 0. So basically my n can vary from 0 to infinity. Okay, and we will come to which are the physically relevant things for me, but this is the range in which n can vary. And if I do this, I can rewrite this in a particularly interesting way. I can rewrite this as gamma minus 2 is equal to 1 by n minus 1. Is that okay? And then I will rewrite this equation as 1 plus 1 by n into kappa divided by 4 pi alpha cube. It's a mistake here. You should have pointed out it's alpha cube here. Oh, sorry, alpha square, sorry. 4 pi alpha square, okay, 1 by xi square d by d xi square rho to the power 1 by n minus 1 d rho by d xi is equal to minus 0. I mean, it may look like tedious mathematics, but at the end of it, you will find a very beautifully simple result. So one is one dimensionless variable I defined as xi equal to alpha by r. I will now define another dimensionless variable theta, which is equal to density divided by the central density of the system. Okay, where rho c is equal to central density. And so I will rewrite this as 1 plus 1 by n kappa k by 4 pi alpha square 1 by xi square. Okay, so before that, let me just simplify this. So it may, no, I'm sorry. I have to say this to power n is equal to. Yeah, this is how we define it. And so I can write this in the following way. This can be written as, so I have d rho by d xi is equal to rho c times d theta to the power n by d xi, which is equal to rho c n theta to the power n minus 1 d theta by d xi. Okay. And so if I substitute all this here, I get 1 plus 1 by n k by 4 pi alpha square 1 by xi square d by d xi square into rho c to the power 1 by n minus 1 times theta to the power 1 minus n d theta by d xi. D theta by rho power, is it correct? Yeah. Yeah. Okay, no. Just a minute. This is a mistake.
Rho c into n theta.
Yeah, then I have to have this one also. I have to have for d rho also. And then I have to substitute from here. So I will have a rho c n theta to the power n minus 1 d theta by d xi. Right? See, this portion comes from rho to the power 1 by n minus 1. And this portion comes from d rho by d xi. All right?
Yeah.
Yes, no?
Yes.
Okay.
Yes.
So what I find here is that this and this will cancel out and leaving me with the expression 1 plus 1 by n k. The rho c will, now the rho c into this will be rho c to the power 1 by n. This n will come out and I will have an n here, leaving me with, and then this divided by 4 pi alpha square 1 by xi square d by d xi square d theta by d xi is equal to minus g rho c theta to the power n. I'm substituting for this one. Here is rho c here. All right. I just substituted for rho from rho c into theta power n. Is that okay?
Yes.
Yeah.
Oh,
Okay.
yeah, got it.
Okay. And so the rest of it is only simplification. I now take this rho c on the other side. I have rho c 1 by n minus 1 into 1 n plus 1, this one, k by 4 pi alpha square 1 by xi square d by d xi. And I will take the g also over here. And I will take this rho c also over here. No, I have already taken this rho c here, right? Yeah. Okay. And then this into xi square d theta by d xi equal to minus theta power n. Okay, so let me just check if this is the correct expression. Just want to make sure. The 9 and then I have okay. Where I have taken alpha is equal to 1. Yeah, that's correct. Okay. So this is my equation. But now I use my freedom. What is it? I have told that alpha has dimensions of length, but I have not yet committed myself to what is the value of alpha. I choose my alpha in such a way such that alpha square is equal to rho c 1 by n minus 1 n plus 1 k by 4 pi g. Then this quantity will become 1. And this equation will reduce to 1 by xi square d by d xi, xi square d theta by d xi equal to minus theta power n. So in other words, I have by scaling the distance and density accordingly, I have been able to reduce this equation to a simple dimensionless equation of this form. And this is the celebrated Lane-Emden equation.
This is supposed to be a very stable condition, right? For any kind of collapsing or sorry, any kind of a gaseous.
No. It depends on various parameters of n and so on.
If I said n is equal to 0, that's.
Oh, n equal to 0. Okay. So when n equal to 0, what do you think it is? See, when n equal to 0, you have theta power 0.
Mm-hmm.
Where is it? Yeah, which it means a constant density sphere. So it is a constant density sphere. Okay.
Isotropic.
Okay. So now so before I proceed with solutions of this one, let us see what is so special about this equation. You see here, what we have shown is, if suppose I have two stars, both have the same polytropic index n. One star has central density rho c1 and another star has central density rho c2. And if I know the solution of this rho 1 as a function of r, since this equation is same for both, by appropriately multiplying by some factors I will get this equation also. So in other words, this whole, I will give you examples to show this. What it says is, it has divided the systems into different classes. Once I solve the equation for one of the classes, I don't have to solve an equation again for another system in the same value of n. The moment I know the value of n for one of the class, I immediately get the solution for everything. Do you understand this?
Okay.
Okay. So because, see here, this equation does not depend on what is the size of the system, what is the central density of the system, nothing. Okay. Because this has been written in certain dimensionless form. Okay. So suppose, for example, I get the solution for this as some theta as a function of xi. Okay. Now, what does this mean? This means it is rho to the power 1 by n is equal to rho c to the power 1 by n times r divided by alpha. Okay. And so it is rho equal to rho c r divided by alpha to the power n. Am I? Sorry, what am I writing? I'm sorry, what am I writing?
Yeah.
Sorry. I'm writing some junk. Sorry. So it says that it is rho of, so I have theta as a function of this one. So theta is, so yes, so it is rho by rho c okay, to the power 1 by n and is a function of r by alpha. So you see,
Okay.
in what way, if suppose you have two systems with the same polytropic index n, okay, polytropic equation is P is equal to K rho power n, rho power, 1 plus 1 by n, rho power gamma. So if suppose I have the same polytropic index n, then the only way things can be different is the value of K. Okay. And what is the value of K? The value of K, if I just substitute it here, will be P equal. So K will be equal to central pressure by central density to the power 1 by n. So in other words, if I have two systems with the same n, this is the only factor by which they can differ. So if I have one system for which I have solved the Lane-Emden equation and I know rho as a function of r, just by scaling r using alpha, I can get the solution of the other system without having to solve the equation all over again. Is it clear?
Yes, yes.
What do you define by class of systems? I didn't get that very clearly.
A class of system means all systems having the same value of n.
Okay.
One
Okay.
polytropic class.
Okay.
Okay.
Wait, one polytropic class meaning it's just because they have ones.
No. So
they can have different K values, right?
Yeah.
Just get that.
So that's what I'm saying. If suppose I have a set of stars, set of system, all have the same value of n. Okay. Then remember, then this equation, the only parameter it depends on is the value of n in this form.
Okay.
So the solution of theta as a function of xi will be the same, whatever be the value of k.
Okay.
So which means that if I have two systems with two different values of k, I know the complete solution of one of them. Just by multiplying by appropriate value of rho c and pc, I can get the solution of the other.
No, just a scaling factor.
It's a scaling factor, exactly. These solutions
Okay.
can scale.
Okay.
That is the advantage of this one. Is it clear, others? Saundarya, Snigdha, Yadil?
Yeah.
Yes.
Okay. No, I will give you some very specific examples for this. This is actually a very important class. I will actually tell you an anticlimax afterwards that these systems not always represent stars. Okay. But why is it important? It is important because if there is a star which undergoes a perturbation, then the path by which it goes from one configuration to another is through this. And that is, I'll come to that in detail. Okay. Yeah. So this is called the Lane-Emden equation. And now what we will do is to solve the Lane-Emden equation. Now the interesting thing is only 3 values of n give analytic solution. And these values of n are n equal to 0, n equal to 1. Again, it has created problem. And n equal to 5. And we will consider specific cases of this. What are these? What are the characteristics of this? So let us consider first the case of n equal to 0. The n equal to 0 case, we have 1 by xi square d by d xi square d theta by d xi is equal to minus theta to the power n, which is equal to minus 1. Okay, because n equal to 0. Okay. Right? Hello?
Yes.
Yeah. So this implies, then this is easy to solve. This will be d by d xi square d theta by d xi is equal to minus xi square, which implies that xi square d theta by d xi is equal to minus xi cube by 3 plus 1 constant of integration. And so d theta by d xi is equal to minus xi by 3 plus c1, giving theta is equal to minus xi square by 6 plus c1 by xi square plus c2. Are you with me?
Yes.
Yes, yes.
Fine. So now, let us now solve this. Remember that I have yet to use the boundary condition. It's just this solution I have used. Now, okay. So now let us see what happens at xi equal to 0. At xi equal to 0, if C1 is not equal to 0, solution is singular. That is, theta tends to infinity, plus minus infinity. And hence, C1 has to be 0 to suppress this. And so I have theta is equal to C2 minus xi square by 6. Now, what is theta? Theta is equal to rho by rho c by to the power n. So, rho is equal to rho c at r equal to 0, which implies at xi equal to 0. Now, theta is equal to c2 at xi equal to 0. But since rho equal to rho c, theta equal to 1 at xi equal to 0. Is that okay?
Yeah.
Okay. And hence it means C2 equal to 1, which means the solution is theta is equal to 1 minus xi square by 6. Is that okay? Now, okay. So now P is equal to K rho power 1 plus 1 by n, which implies that rho is equal to P by K to the power n by n plus 1. For n equal to 0, rho equal to constant. This is what Anirudh was asking earlier. The n equal to 0 case corresponds to a constant density sphere. All right?
Yeah.
Hey. Okay. Now, what about P? Now, this is constant. This is constant. So let us look at it this way. So I have P is equal to K rho power 1 by 1 plus n, which is equal to K rho C to the power 1 by 1 plus 1 by n times theta into n plus 1. Because rho by rho C is equal to theta power n. Is it okay?
Yeah.
And hence, for n equal to 0, P is proportional to theta. Okay? Now you may wonder that when n is 0, what about this rho C? The exponent goes to infinity, right?
Yeah.
Okay. Now the answer to this is the following. The devil is in K. Remember, what is K? K is equal to PC by rho C to the power gamma, because P is equal to K rho power gamma, which is means equal to PC to the power rho C to the power 1 by 1 plus n. And so this quantity and this quantity gets cancelled, and P will be equal to PC times theta. Do you get it?
Yes.
Okay. So what it means is this theta which you have calculated is something proportional to pressure. And so it means that the pressure is equal to PC times 1 minus xi square by 6. And so I have P is equal to PC 1 minus R square by alpha square 6. Now, what is alpha? Alpha, we know, was, we had got the alpha, right? Here. Okay, so here we have the alpha. So it means that if suppose you have two systems, with same n, but different PC, rho C, etc., in the form of theta equal to 1 minus xi square by 6, the solutions are the same. So by using the appropriate PC and rho c, I can get the solution of both of them from here. This is the scaling thing which I was mentioning. Is that all right?
Yes.
Okay. Let me. Okay, so I'll give some examples of this. Okay, I will summarize it in the notes anyway, all these things. Next, let me consider two values of n, and then I will tell various properties of this. Next, consider n equal to 2. Now the n equal to, sorry, not n equal to 2, n equal to 1. Now for n equal to 1, I can write 1 by xi square d by d xi square d theta by d xi is equal to minus theta. Okay. Let me substitute for theta as some function chi divided by xi. And so, if I divide it by so xi square into d by d xi, multiply this one, I will have xi d chi by d xi minus chi is equal to minus theta. And so this will be equal to 1 by xi square d chi by d xi plus 1 by xi d2 chi by d xi square minus 1 by xi square d chi by d xi is equal to minus theta. And what I see here is these two beautifully cancel out. And these two cancel out. What have I done? Yeah. Cancel out. And then I will write this as 1 by xi d2 chi by d xi square is equal to, I will substitute it back as this thing. Oh, sorry. And so this implies that d2 chi by d xi square equal to minus chi. Do you recognize this equation? This is the, yeah, this is the dream equation for all theoretical physicists, simple harmonic motion. And so I have chi equal to A cos xi plus B sin xi. And so the theta is equal to A by xi cos xi plus B by xi sin xi. And now I need to solve for these. And once again, I appeal to my central conditions. As xi tends to 0, sin xi by xi tends to 1. But cos xi by xi tends to infinity. Hence, for physically acceptable solutions, I need A is equal to 0. And so I have theta is equal to B sin xi by xi. But I know that at xi equal to 0, theta equal to 1 as before, because rho equal to rho c. This implies that B has to be equal to 1. So the solution for the Lane-Emden equation is theta equal to sin xi by xi. Okay? Are you with me? Okay.
Yes, yes.
What does this mean? Now let us try to look at it. Once again, I have P equal to K rho power 1 by 1 plus 1 by N. And so P is equal to K theta to the power N plus 1 by rho C to the power minus, sorry, rho C to the power 1 plus 1 by N. Sorry. Yeah. And P is equal to, we know that this is equal to PC by rho C 1 plus 1 by N theta to the power N plus 1 rho C to the power 1 plus 1 by N as before, and these two cancel out. And as before, we have P is equal to PC theta to the power N plus 1. For N equal to 1, P equal to PC into theta square. Now, what does this mean? It means if suppose I have yeah, okay. So yeah, so if I have a system for which at R equal to R1, P equal to P1 at some radial distance. Okay. And both belong to N equal to 1. And I have another system, and I want to find out what is the value of pressure at R equal to R2 for the second system, system 1, system 2. Okay. Then what do I do? For both these systems, I can calculate the value of alpha, and I can find out the factor by which R has to be multiplied to get that pressure here. This is again the thing about scaling relationship, which I was telling you. Okay. For example, I have P is equal to PC sine of xi by xi, which is equal to PC sine of R by alpha by R by alpha. Okay. Now for these two systems, what is different is alpha, right? Because alpha has to do with, yeah, rho C, K and K. These are the only two things. So these two can be different. And so I have alpha rho C1, K1. Okay, so I have alpha equal to rho C1 by, was this the expression? I should just copy it here. Okay. So it means that if suppose I have the second system, so I have the system 1, I have alpha is equal to rho C1 n plus 1 K1 by 4 pi G square root. I mean here 1 by n minus 1. This is alpha 1. Okay, this is for alpha. The second system alpha is the same thing for 2. So it means these are the two different scaling ratios required to convert Xi to R. So once I know one of them, I can calculate the other. Is the basic philosophy clear why this Lane-Emden equation is important?
Yes, sir.
Okay, because it just simplifies it, because it breaks it down to specific classes of solutions so that you don't have to solve it for every case, but I just have for every system, I just have to solve my equation for one member of a class and all the other solutions will be there. Okay, I will stop it here. Okay, so next time I will go over some more gaps in this Lane-Emden equation, and I will actually calculate how to calculate the mass of the system, radius of the system, everything.
Stay.
Huh?
So most of the stars will be having equation of state of this form, like P equal to rho to the power some gamma or something.
No, most of the no.
The equation of state of most of the stars will be of
No,
this
no, no.
form
It is
or-
not. It is not. It is in
No.
fact it is not.
Not like that.
I mean, the reason is okay. You know, there are like for example, there will be like there will be some stars which may have it, but what happens is I will come to it. Actually, if you calculate this one, and you can calculate the central temperature. When you calculate the central temperature, that temperature will come out to be very large compared to fusion temperature. It means that this cannot define all the main sequence stars. However, if you have a main sequence star and you perturb it, before it goes to another stable configuration, it will be in this Lane-Emden kind of a form. I will come to that actually, how much time scale it takes, everything.
Okay.
Okay.
Meaning
How
this,
central
you can say that
density
this is some.
actually calculated?
Sorry, what is it?
May I go ahead?
Yeah.
Yeah, go ahead, go ahead.
So how is the central density actually determined? Because that seems to be very important here.
Oh, yeah. So that has to be modeled.
But how? Like a different set of principles for that?
Oh, that you actually do the kind of okay. So one thing is so you know that this central region, the temperature is governed by fusion temperature.
Yeah.
Which is around 10 to the power 7 Kelvin.
Okay.
Okay. Now it means that since it is an ideal gas, you know the pressure density relationship for the center.
Okay.
Then you have some bounds on the pressure.
Okay.
Okay, so these are the the problem with stars is that you can only directly see only a thin layer below the surface. So everything has to be determined by modeling.
All right.
Okay. Yeah.
Yeah, I have one question.
Yeah.
So you talked about that a star, when it's perturbed and it's transforming to another stable state. So there will be a certain duration of time where this will
Yes.
be following the Lane-Emden equation for a certain polytrope,
Yeah.
for a certain n value. Okay. So
okay. So it's something like this. Let me give you since you're asking.
It's like kind of like a metastable state. That's what
Yeah, exactly. So suppose it is like this. Then suppose this is log of mass versus log of R. And suppose like this, it is the polytropic thing. And the main sequence will be coming like this. Okay, suppose the star is over here. And suddenly what you do is you dump some mass in it. it immediately increases here. Now, for
Okay.
the equilibrium thing, it has to move here. But if you calculate the time taken for it to move from here to here is much, much larger than for it to move from here to here. So what it will do is it will first go here, and gradually later move to this equilibrium afterwards.
Okay.
So it is in this time, when it is in this one, that Lane-Hampton equation is very valuable.
Oh, okay.
Okay.
Will you be
also
covering?
Hmm?
Yeah, go
Sorry.
ahead, sorry.
So also there is another thing that, you will find that how, okay, I will just come to it next time, because, there's a whole set of things now. How you can, given a value of n, how you can calculate the mass of the system for a given radius and so on.
Hmm.
From that, it will be clear. So what
Okay.
I'll do is, next time, I will summarize the results here and then take up some. So what I have been claiming is that there is a scaling relationship possible. Now I'll give you some example of how, knowing the details of a star of one of the classes, I can find out the details of another star belonging to the same class, that is belonging to the same polytropic index.
Okay.
Okay. Yeah. Tell me something. I mean, is it useful to upload this recording here? I mean, because there's a lot of rough work which has happened. That's why I'm asking.
No, that's fine. I think we can go for
fine.
it.
Fine. Okay. And I will anyway upload the proper notes also. So. Pardon? Hello?
That's someone. That's someone in the background.
Okay. Okay then, huh? Thanks.
Okay, sir.
Yeah.
Okay, Sesh. Thank you.
Acha, Harish, I will send the reco today.
Yes.
Yeah. Okay.
Bye. Bye.
Bye.
Hmm.